Hello there, Calc students watching this as a screencast. If you were absent for the February 20th mock exam, you're watching the hour in which it's our debrief session where we're going to cover logistic growth, parametric, polar, and any additional topics that we have time to cover today. So we're going to start with logistic growth. It's from a 3 Blue 1 Brown video titled Exponential Growth and Epidemics for us to understand the basics of logistic growth, which is basically all we need to know for the AP exam. So let's see what we have, what we can see here from this video.
Even in the most perfectly pernicious model for a virus, which would be where every day each person with the infection is exposed to a random subset of the world's population, at some point, most of the people they're exposed to would already be sick, and so they couldn't become new cases. In our equation, that would mean that the probability of an exposure becoming a new infection would have to include some kind of factor to account for the probability that someone you're exposed to is already infected. For a random shuffling model like this, that could mean including a factor like 1 minus the proportion of people in the world who are already infected. Including that factor, and then solving for how n grows, you get what's known in the business as a logistic curve, which is essentially indistinguishable from an exponential at the beginning, but ultimately it levels out once you're approaching the total population size, which is what you would expect. True exponentials essentially never exist in the real world. Every one of them is really the start of a logistic curve. Now, this point right here, where that logistic goes from curving upward to instead curving downward, is known as the inflection point. There, the number of new cases each day, represented by the slope of this curve, stops increasing and instead stays roughly constant before it starts decreasing. So, one number that people often follow with epidemics is the growth factor, which is defined as the ratio between the number of new cases one day and the number of new cases the previous day. So, just to be clear, if you were looking at all of the totals from one day to the next, then tracking the changes between those totals, the growth factor is a ratio between two successive changes. While you're on the exponential part, this factor stays consistently above 1, whereas as soon as your growth factor looks closer to 1, it's a sign that you've hit the inflection. This can make for another counterintuitive fact while following the data. Think about what it would feel like for the number of new cases one day to be about 15% more than the number of new cases the previous day. And contrast that with what it would feel like for it to be about the same. Just looking at the totals they result in, they don't really feel that different. But if the growth factor is 1, it could mean you're at the inflection point of a logistic, which would mean the total number of cases is going to max out at about 2 times wherever you are now. But a growth factor bigger than 1, subtle though that might seem, means you're on the exponential part.
Okay, I think that's enough, to be honest, because um, he just said that 1/2. When you're at that point, you're at the 1/2 point, and that's what logistic curves are about. So for a moment, you're going to see my backyard upside down. There you go. Actually, before I write down the notes, we can find these notes. And then let me show you where you can find these notes that I'm about to give you. You can find them in the... Uh-oh, I'm freezing up. Okay, so in this February 17th post I gave you a Alcocer handout. And if you open that up, hit Control F and type in logistic. I gave you the AB, but that should have it. There's some good stuff in here if you haven't looked through it yet. I don't know why it's not reading logistic. I'm spelling it wrong. There we go. Okay, so logistic growth, it's on page 51 of that sheet. dy dt, the rate of change, thanks Terrence, equals k, a constant, times y, which is the amount at that moment, whether it's population or number of zombies in a city, times a minus y, where a is the carrying capacity, the population, the maximum value y could be. And we see the inflection point happen at 1/2 a. The slope is the steepest at 1/2 a. And he just was showing that. Grant Sanderson from 3 Blue 1 Brown was just discussing that, where we see concavity go from positive to negative, meaning the slopes are increasing until that point, and then the slopes are decreasing. When the slopes are increasing till a point, that means that point has the maximum or locally steepest slope. We talked about this a lot when we graphed derivatives in class. So this is what we need to memorize. The rest of it down here, you don't need to memorize. This is not part, this is solving the differential equation, which never shows up on the AP exam. We need not know how to solve it. If you're interested, by all means. What we need to know is everything until you see the 1/2 a. So let's write all of that down. Logistic growth. I like to use P for population instead of Y. So I'm going to say D capital P over DT equals K capital P times capital A minus capital P. And it's called a joint variation. It's a joint variation because, like the beginning of the video I just showed you, it behaves exponential, right? An exponential growth function, its differential equation looks like dy dt equal ky without the a minus y. And so when y is really small, a minus y is just another constant. And so you see a logistic growth curve look exponential at the beginning. But as y increases, this a minus y factor becomes relevant. And as y increases, a minus y approaches 0. And so the slope is a maximum when y is 1/2 a. That's when this product that we see here is going to be, the slope is going to be maximum when y is 1/2 a. And then once y bypasses 1/2 a, this a minus y term approaches 0 and it levels off the logistic curve toward the carrying capacity or population. This model, of course, works for epidemics. It also works for various technological innovation, where we see perhaps, like the growth of, say, electric vehicle adoption starting out slow but exponentially increasing each year. And then once that technology reaches its, maximum that we can figure out, maybe it's density of a battery. But unless you invent a new battery like Tesla is. Anyways, so we have dPdt equal Kp times A minus P, where A equals carrying capacity or maximum value. And that's just a model. Sometimes the actual data goes above the carrying capacity, but there are forces that bring it back down toward the carrying capacity. Like if the population of a fish in a pond gets above the carrying capacity, maybe it's going to run out of food and that population will then decrease back down, that type of thing. So A is the carrying capacity, and maximum slope / maximum dPdt at t equal a over 2. Pretty sure that's all you need to know. Maybe we could draw a little graph about it to document that. Comments or questions, AP Calc BC, about that? dp/dt is the rate of change, and the rate of change is dependent upon the amount, that part makes it exponential, multiplied by the carrying capacity minus that amount. That's the part that makes it a joint variation. That's the part that makes it logistic. Right? If it's dp/dt, if it's that, that's indicative of straight up exponential growth equation, because if we solve this, we move the t over, we divide the p, we integrate, we get natural log of p equal kt. We solve for p by converting it to an exponential, and so you get p equal e to the kt plus the constant, and you do all that work that we did when we were in chapter 5, I believe, right? But this makes it logistic, and we don't need to do any math on it. We just need to know how to like restructure the form if the form isn't like this, because maybe this a value is not a, but it's 1, and there's like a p divided by a number. Well, then it's just algebra. You're moving around the numbers, and my goal is for you to rewrite it like this, or if the answer choices aren't like that, it's just some algebra to make it look like the answer choices. So let's go to the problem. I'm not seeing questions or hands being raised. Please raise your hand if I can help you. Let's go to the problem that was logistic. Well, it's not KT, it's not KY, so it's one of these here. And notice that C is dealing with the input variable T, so it's not C. D has a Y here, but then it has a T here, so it's not that. So it's E. The answer is E.
Mr. Gordon, is every logistic growth problem going to be like this? Because then it is just like just a formula, memorizing the formula, just kind of thing.
Thank you, Joseph. If you wanted to see more possible ways that these questions have been asked in the past, what you need to do too many tabs. What you need to do is go. I've never seen Logistic. I don't think I've seen them in free response. You can try to find them there, but I've mostly seen them here. And what you want to do is go to the index, right? And in the index, you can hit Control F and type in Logistic, and you just have to spell it right. And you can find some extra ones. So, like in 2008 BC 24, 2008 BC 24, 2008 BC number 24. So here's one that looks different. So the concept is the same. We only need to know the notes I gave you. If you know the notes I gave you, you can answer this question. What's A in this case? What is the carrying capacity?
200.
Exactly. So now, what do we not know? We don't know K, right? So you can say dp/dt equals Kp times parentheses 200 minus P, expand it out, and see which one could be that form. And there's only going to be one. Go ahead and do it right now. Look at the structure. You have 200 kp minus kp squared. Well, that means the constant in front of the p is going to be 200 times bigger than the constant in front of the p squared. That pigeonholes it to a. You might have been saying, oh, it might be a or b because I know it's a negative p squared term. Do you guys see what I'm saying here? Kp times 200 minus p, distribute, rearrange in kind of standard form. So you have a negative p squared for sure. So that means the answer could be a or b. And then you look at the constant and say, well, it's got to be 200 times bigger. So it can't be the 0.1 and 0.001. That's not going to work out because that's 100 times bigger. Does anybody need more time there or have a question on how they can answer logistic questions and where they can find more of them if they want to practice them?
Where can you find them?
Joseph, where can you find more questions if you want to practice more logistic growth questions?
You go to the Google form and then you go to the
Class resources,
resources.
multiple choice index, open up the index, Control F, type in the topic you want to study. It'll tell you what test and what number to look at from these released tests.
All right, thank you.
You're welcome. Okay, so I think now the next would be parametric. And so with parametric equations, you're involving yourself with an auxiliary variable, a tertiary side variable. X and Y are independent of each other, but they're both dependent upon an auxiliary variable. Usually we think of it as time. I like to think of it as the Etch-a-Sketch functions. And if you've used an Etch-a-Sketch before, one knob affects the horizontal movement of your drawing, and another knob involves and affects the vertical nature of your drawing. And so what parametric equations allow you to do is create more exotic looking curves than just the standard functions that pass the vertical line test. So you can graph circles, loop-de-loops, cycloids, and there's a bunch of other fancy names for these things. So if y equals f of t, then f prime of t is vertical speed. And if x equals g of t, then g prime of t is horizontal speed. So we're now talking about vectors, and for all intents and purposes. If you have your stuff you must know cold sheet handy. There's going to be some areas where you're going to be able to say, okay, I know this one now. Like this part of the worksheet I haven't been able to answer before, but now I get it. So let's imagine some vectors representing vertical and horizontal speed. So let's say we have, an airplane that's lifting off. So it has an actual speed that's diagonal. Anything that has diagonal speed can have its speeds analyzed with its horizontal and vertical components separate, and that combination creates the actual speed. You'll have horizontal and vertical speed, but together makes this actual speed. So you can draw that and that, and so we would say this is g of t, g prime of t, or maybe we could just call it dx dt. Perhaps that might be nicer. We have vertical speed, f prime of t, or dy dt. And when we're talking about speed, we're talking about a scalar. We're talking about a numerical value, and direction isn't really important. So we're actually looking for the magnitude of this vector. How do you find the magnitude of this right triangle's hypotenuse?
Do you use Pythagorean theorem for this?
Exactly. And that shows up on page 1 of your stuff you must know cold sheet. And for those of you that went through the Steno book project, you've had a nice introduction to this, and I truly hope that you utilize the textbook still. I hope you kept it, and if you didn't, you could go back and check it out for a couple more months, because I think um, that book is well written. The introduction set the stage, and can really supplement everything that I tell you. I hope it, and if I'm missing something or if you have something to add, always you are welcome to do so. So how about slope? Slope kind of gives us the direction. And so slope is rise over run, right? So the slope is going to be rise over run. The slope is dy over dt divided by dx over dt. Think about it for a second. Doesn't that equal dy over dx if you simplify it? Multiply the reciprocal, and you get dy over dx. And so the velocity vector it kind of looks like a coordinate pair, but instead of parentheses, you use these like pointy brackets or a greater than less than symbol, and you kind of write it as horizontal speed comma vertical speed, and so that kind of helps you draw the velocity vector correctly. So like maybe this velocity vector would have been like maybe 2 comma or 4 comma 2 or something, you know. So um, what's nice about the horizontal and vertical vectors is that they're horizontal and vertical. You know how to draw them in the direction that you want. They're orthogonal. They're perpendicular. Regular functions are parametric if you just let t equal x, technically.
Mr. Gordon, I have a quick question.
Yes, sir.
How would you find the second derivative of this parametric?
Well, I'm curious to maybe if you could rephrase what you mean, because um, everything is kind of separate. So if you wanted to find the rate of change of the horizontal rate of change, you could just take the second derivative of the derivative to find those. There isn't, I mean, it's hard to draw an acceleration vector. That's not something I'm really familiar with, I think. But if you wanted to, you could take the second derivative with respect to t and the second derivative with respect to t. You can find you can find the acceleration of the horizontal and vertical components separately. That'd be just fine. Is that what you're asking about?
Kind of, because I remember like when I was like I watched a video about this, and I remember they said something where you have to like you take the second derivative of the bottom and leave the top the same. You get the second derivative or something like that. So I was a little confused on why you would do that. So
if you can post that link to me, I can give you better feedback. But I'm trying to give you the AP Calc BC version of these notes so that we can earn our 5. And if we want to explore further, come to my office hours and we can delve into it a little bit more. Does that make sense?
Yeah.
Okay, so let's see if I need to add anything more to these notes by looking at some of the practice problems that involve parametric. So they often give you one at the beginning. Here's one. Number 2. Okay, so number 2. The position of a particle is given by these equations. At which points is the particle at rest? How many of us got this one without knowing what parametric equations were? And if so, what did you do? Wait, Hohan, what's them? I hate pronouns.
the two equations like x of t and y of t.
That would be finding when the position is at the origin. That's not when the position's at rest. We want the particles at rest. At rest means you're not moving. Moving is a rate of change. So you want to take the derivatives and set them equal to 0. Not necessarily where m equals 0, because when m is 0, that's the slope is 0. That means the vertical speed is 0. That means the particle has a horizontal tangent line. We're looking for when the particle is not moving left or right, nor is it moving up or down. It's instantaneously motionless, which is kind of paradoxical, because at any given moment, something is motionless because a moment is timeless. Anyways, I think you know what I'm saying. So set the derivatives equal to 0 and solve. And then that gives you the t value that you need to plug into the original function to find that position in which it's at rest. Is the answer D? No.
It's A.
Okay. So you set the derivative equal to 0. You take the derivative, you get 3. Sorry. Yeah. When you take the derivative of y, you get 12 minus 6t. And so 0 is not an answer. Never mind. Sorry. So 12 minus 6t, set it equals 0, you get 2. Is t equal to a solution of x prime of t equals 0?
Yeah.
T equal 2. So then plug in 2 into both. You get 8 minus 12 is negative 4. And then you're done because that's the only answer with the next value, negative 4. You don't have to find the y value. You move on. It's multiple choice. Maybe you're not so much an auditory learner. Does anybody want me to show this under the document camera? We'll title this Parametric Example 2012 BC number 2, multiple choice. 1. No, it's number 2. Position is x of t equal t cubed minus 3t squared. If you are good with this one, look around and see if you can find another parametric for me to deal with.
You share your screen, so go ahead.
Yeah, I'm writing down the question first.
Oh, you are? Sorry. Thanks.
Yeah. When is particle at rest? All right, I think I've paraphrased the question good enough. We have a position of a particle determined by those individual x and y coordinate. So, I mean, for those of us really trying to grapple with what's going on with this, the horizontal position is dictated by this. When you plug in t equals 0, you get an x value of 0. When you plug in t equals 0, you get a y value of 0. So this particle is at the origin when t equals 0. When you plug in 1, you get 1 minus 3. The particle's moving to the left as t increases at the beginning from 0 to 1. From 0 to 1, the particle's moving to the left. Because as you plug in values from 0 to 1, 0 cubed is smaller than t squared because a fraction cubed is smaller than a fraction squared. And so therefore, this thing is larger than that thing as t goes to 0 to 1. So we're moving to the left. When you plug in 1 here, you get 12 minus 3. So the particle is moving up and to the left as t goes from 0 to 1. That really isn't relevant, but just to give us an idea of how do we plot these points, what's going on with this particle? Well, the particle's doing something weird. It's not moving from left to right necessarily. It's being dictated by these position equations. Individually, Etch-a-Sketch, x and y are individual movements. Put them together, you have a single particle moving. When is it at rest? It's at rest when x prime of t and y prime of t equals 0. It's at rest when the horizontal and vertical velocities are 0. Okay, well, what is x prime of t? X prime of t is equal to 3t squared minus 6t. So when you set that equal to 0, you get 3t times t minus 2. I think I did that right. Yes. Y prime of t. So you have zeros at t equals 0 and 2. Y prime of t equals 12 minus 6t. When does that equal 0? That equals 0 when t equals 2, right? Because you need this to equal 12 for 12 minus 12 to be 0. So t equal, it's at rest at t equal 2, not t equals 0, because when t equals 0, it's not moving left or right, but it is moving straight up and down. When you plug in t equals 0, you get a vertical velocity of 12. Ryan and Pablo, is this helping?
Yeah.
Okay.
Thank you. Yeah.
So t equal 2 is what we want. So we plug in. So we're at rest at t equal 2, and that position is x of 2, which equals 8 minus 3 times 4, which is negative 4. And so now we're done, because that's the only option when x equals negative 4. There's only one option. If there were two options for x equal negative 4, we'd have to plug in t equal 2 at the other one. And so I guess just to be thorough, because we're not getting timed, we could throw it in and find it. Did anyone look through the test and find another parametric example that we should cover?
Mr. Gordon, I have a question
Go ahead, Joseph.
for this problem specifically. So, I'm curious how this problem specifically is related to the notes that we took, because we mentioned about like the slope being the derivative of y over like the derivative of x, but we didn't necessarily do any of that, unless if I'm mistaken. Like, I'm just
Well, we want the velocity vector to be 0.
yes.
So we need the vertical speed to be 0 and the horizontal speed to be 0. So we didn't really need to go below those notes. We're done with this. This part of the notes answered it for us. You know, a particle is at rest in a two-dimensional plane, that is, when it's not moving up or down and it's not moving left or right. Because if you're moving diagonally, you're moving up and down and left and right. You're stuck. Now, if you have a third dimension, you could dig into the paper or jump out of the paper, but we're not in 3 dimensions right now.
Yeah, okay, that makes sense. Thank you, Mr. Gordon.
You got it. I hope we can realize that what we are doing with single variable calculus, 2 dimensions, is simplifying the real world. The real world is 3-dimensional. At least our physical world is 3-dimensional. There's very possibly more dimensions that we maybe can perceive subconsciously or on a biological cellular level that we don't consciously deal with on a day-to-day basis. But in the physical world, it's 3-dimensional, and those dynamics are so complicated that we must spend a lot of time first analyzing 2-dimensional work and then expand it to 3-dimensional work. And that's where you get into Calc 3 and Calc 4 and your differential equations at university. But to think that you can get by now, some of us have been able to get by through our mental capacity, and some of this work we're not putting on our paper, but just know that it gets magnitudes more difficult just by adding one more dimension to this thing. And trying to understand how the air currents or water currents in oceans, throwing that extra axis, so to speak, into the mix. What is nice about it, though, is that we can these fundamentals, though, directly apply to the more complicated stuff. So whenever things get tough, maybe hold constant one variable. When you get into your future, if you're stuck on something, hold one variable fixed and then analyze it as a two-dimensional problem, and then bring that next dimension in and see if it helps. That's just my word of advice and for your future self. Is there any other questions on this problem? Are there any other questions from this mock exam that deal with parametric equations?
It's not. I have a question, but it's not like about about this question. I just want to. Do you know where I can find some with 3 variables? Like, do you have an example problem I could try?
Well, I have my notes from Cal Poly sitting around in a box somewhere. Yeah, I probably could, but that would probably go beyond the objective of this morning.
Okay.
I think 3 Blue 1 Brown very well could have something for us in there. If we look through his videos, we know he does good stuff. If we go back to school, you can pop into my room and I have some books that I can share with you that you could borrow.
Okay, cool.
Yeah. So let's actually throw something else into our notes. Let's go with distance travel. Well, distance traveled, I think it makes sense is the integral from A to B of the absolute value of velocity with respect to time. So, right, distance traveled, if you're running around a track and you start and stop in the same location, that doesn't mean you didn't travel any distance. So that's why we have to have the absolute value there. So if you want to mark, we need absolute value in case you turn around and run backwards. It doesn't mean that distance is being negated, so to speak. So that's the simple way to write it. But then here's the actual way that you can solve a problem with it. It would be, well, so the magnitude of the velocity vector is the same thing as the absolute value of v. So, distance traveled is the integral of speed. And I think that's something we've known since before we hit parametric, right? Like the integral of velocity gives you distance traveled. And now we're just doing it with regard to parametric. And so that would be the integral of the square root of dx dt squared plus dy dt squared with respect to t. This is also, I believe, the same formula for arc length. It is. Look on your one box up. Okay. So arc length also. Which I hope makes sense. Arc length means just like the distance of a curve, and the distance of a curve could mean, if you're a particle traveling on that curve, well, the length on that curve would be equivalent to the distance traveled by a particle on that curve. if there's no more parametric equations on this one, I'd encourage you to look at more in the other ones given through the index, and then come into office hours if you need help. Ask Mr. Calculus has the solutions for those other released tests as well, like the one I sent you for 2012 for the one we're dealing with. So if you look at those past exams and you know the answer from the index, and you're having trouble seeing it, of course, I can help you in office hours, or you can research Ask Mr. Calculus as well. Let's go into polar. I have a feeling we'll do these notes again because there'll be people that weren't in this one, and seeing it over and over again is a nice way to learn it and practice it. So the coordinates are r comma theta, where r equals distance from origin. So think radius, distance from origin. And theta equals angle in standard position. So let's just draw a random spot here. And we're in a coordinate plane. Right, so you have a theta here, x value here. Well, r comma theta can be superimposed on an xy plane. So we can convert to parametric. Right? Like this is a right triangle, and r is this distance. And so we're going to have an x and a y corresponding to that point in space that we call r comma theta. So we know that x squared plus y squared equals r squared. We know that sine of theta is y over r. So now that is a function of theta. R sine theta is a function of theta. We're turning it into a parametric in terms of an auxiliary variable theta instead of t. Cosine of theta equals x over r, which implies that x equal r cosine theta. That's another. So now we've turned it into parametric. Remember, or note, R is defined as a function of theta already. Okay, so as you look at this, you're going to be given a function for R in terms of theta. So when you see y equals r sine theta, you can replace R with whatever it's defined to be in terms of theta to begin with. And so I hope this kind of makes sense. Like, you have R as a function. If you multiply it by sine theta, you're projecting it like onto the y-axis. You're whatever R is at that moment, multiply it by sine of theta, and boom, you've got the vertical aspect of that point that you're at in space. If you have your function R and you multiply it by cosine of theta, boom, you've projected that point on the x-axis, and now you know how far away from the origin it is horizontally. Does that help kind of with this idea of how, and I know it's new, so whenever you approach a polar problem, we could turn our calculators into polar mode and we can visualize it. It's quite complicated, and I don't want us to necessarily delve into it right now, because oftentimes you don't need to do it for the AP test. You do need to do it to be able to visualize and understand what the heck you're doing, so I don't want us to not do it. But in terms of gathering strategies to do well here, I think we might be ready. We're almost ready to go to a problem, but I think we need to answer a few more areas that we need to work on. So imagine that you've got this particle in space. When theta equals 0, it's on the x-axis. And as theta increases, r kind of changes length, and it kind of creates a curve, and it's kind of circular. How do we find areas of regions? It's a very common question on the AP exam. First, let's recall areas in normal function mode. Areas in normal function mode involve adding up a bunch of little areas of rectangles. Area is the sum of little rectangles. An integral by definition is the sum of things. And whatever those things are, that's what the expression is telling you. Sometimes we're finding volumes, and we're adding up a bunch of volumes of little cylinders, or we're adding up a bunch of volumes of equilateral triangles or semicircles. We did a lot with cross sections this year. And that all stemmed from the idea of finding areas of two-dimensional regions by adding up rectangles. That got us started, and then we took those rectangles and we revolved them around axes if we wanted discs or washers. We had figures come out of that region if we wanted to add up other types of cross sections like triangles and semicircles. Here's how it relates to polar. let's imagine it like starts here at r comma 0, and then it ends here, and we'll call it A, and it ends here at r comma B, whatever that, it, of course this A is 0 and this B is pi over 2, but let's just make it arbitrary. Instead of adding up areas of rectangles, we're going to add up areas of sectors of circles, like slices of pizza, which I am going to order in about an hour. Draw a little sliver of a sector of a circle. It's just brilliant. I mean, integrals are limits, right? They're limits as the numbers of something goes to infinity. Here we were able to find the area of a weird looking region by adding up infinitely small rectangles. So it's really a limiting process. It's the limit, as the number of rectangles goes to infinity, while at the same time the width of those rectangles go to 0. So the same thing's happening here. We're adding up a bunch of little sectors of circles, and we're trying to find the limit of what those sums add up to when we let the number of sectors go to infinity, and the size of those sectors, the theta value here, this theta value is a little nudge, d theta. It's a tiny little theta. This, of course, is r at any given moment. Well, the area of a sector of a circle is the area of the whole circle times the fraction of the circle you're taking. It's a percent symbol, but isn't a percent symbol a fraction symbol? So I'm going to think of it as like a fraction. If I wanted the area of a half circle, it'd be the area of the whole circle times the angle that I'm taking over 2 pi. What's the angle for a half circle? It's 180 degrees, or pi. Pi over 2 pi is 1/2. The area of half a circle is pi r squared over 2. Really, this should actually just be an angle. So let's just erase it and write d theta. I think what I meant to say was pi r squared times the fraction of the circle you're taking. This whole factor should be the fraction symbol I put in. So this is d theta. And so the area of the whole thing is, and this simplifies, right? The pi's cancel. So you get 1/2 r squared d theta. That little sector is 1/2 r squared d theta, and we're going to add up a bunch of them, so we put an integral down. A to b 1/2 r squared d theta. That's it. If you did the Steno book project, you've already done this, but now I got to at least narrate it for you. So now, what problems involve polar coordinates on your practice test that we just took? 91. Okay.
Wait, that might be polar curves. It might be different.
It's no, yeah.
I don't know.
Polar coordinates, curves, and equations, if you want to title it. Yeah.
Okay.
Okay, so polar example 2012, number 91. Oh, yeah, we could also add tangent line. Slope, right? Slope is the tangent line. So I don't like writing on the back. Let's just throw it in right here with a different colored pen. So the slope it's still dy over dx. But in order to get dy over dx, it's dy over d theta over dx over d theta. It's the same as it is for parametric. It is kind of long, but this is what it is shorthand. Like if you wanted to, what we would have to do is do dy over d theta here is product rule, because r is a function of theta, so it's going to be first times root of the second plus second times root of the first. That's dy d theta. And then dx d theta is first times root of the second plus the second times root of the first. I don't often think you need it that much on the AP exam. And if you do need it, I imagine you could use your calculator to do it. Okay, Keon, and let's cross that bridge when we get to it on more practice exams. We get more exposure. We know what we need to work on. Okay. So this polar example, and let's write it down. The figure above shows r equal 2 cosine of 3 theta and r equal 2. Do you notice r equal 2 is the curve where the radius is always 2? That's a circle. It's kind of like the line y equal 5. It's horizontal because it doesn't matter what x is, the output's always 5. Same thing here. R equal 2 is a circle because it doesn't matter what theta is, your distance from the origin is going to be 2. So the sum of the areas of the shaded regions is going to be the whole area circle minus the non-shaded region. So let's just sketch the region. So we got r equal 2. And we got r equal 2 cosine of 3 theta. So what happens when you plug in theta equals 0? When you plug in theta equals 0, you get cosine of 0, which is 1, and 1 times 2, which is 2. So this curve starts right here. And when you plug in, say, pi over 4, cosine, when you plug in pi over 4, you get 3 pi over 4. Actually, let's plug in pi over 3. When we plug in pi over 3, 3 times pi over 3 is pi. Cosine of pi is negative 1. And so when you have an r value that's negative, when we plugged in pi over 3, we should be outputting here, but our r value is negative, so we output in the exact opposite direction. So this point right here is when theta equals pi over 3 because the r value is negative. So the curve went from here along here to here from 0 to pi over 3. R equaled 0 whenever cosine equaled pi over 2, right? So you can think about what value you need to plug in for theta to make the argument pi over 2. I think it's pi over 6. So when theta equals pi over 6, r equals 0, you're hitting the origin. So here's some 0, theta hits pi over 6, theta equals pi over 3. And so it kind of curls around like this. Okay. Let's draw it. And let's label those things that we just talked about. We'll probably finish at 12:05. Thanks for your extra time. So it starts here at 2, 0 for r, theta. This is my r, theta, not my x, y. It curls up, and I'm going to put arrows to show the direction of this particle, if we're going to think of it as a particle. And then it goes like that. And this point right here is -2, positive pi over 3. Again, because if we plug in pi over 3, we get 3 times pi over 3, which is pi. Cosine pi is -1, so r is -2. And whenever you get a negative value for r, you spit yourself in the opposite direction you're supposed to be. And then it curls back around, hits this point, and then gets back to where it started and just continues to loop along there. That was not a great drawing, but it's going to have to do. So if I can find since these are all symmetrical, they're not only symmetrical as 3 different things, but they're symmetrical as 6 different half things. So if I can find the area of this half piece, and this point right here was 0, pi over 6, I can use that symmetry to find the area of this one little sliver and multiply that area by 6. So area of the shaded region is going to equal pi r squared minus 6 times the integral of 1/2 r squared d theta from 0 to pi over 6. I think I'm saying it the best I can. Because of symmetry, the area of this red shaded part times 6 gives me the total non-shaded area that I need to remove. Constant multiple rule. I try to do as much as I can before pushing buttons in the calculator. So I've got 4 pi minus 3 times the integral from 0 to pi over 6 of r squared, which is going to be 4 cosine squared of 3 theta with respect to theta. Push the buttons. Do you get the right answer? You don't need to be in polar mode. You can be in regular function mode, math 9. Oh, some of you still need to write that. So yeah, I'll leave it open for you. Here you go. 4. $11.519. Uh-oh. Where did I make a mistake? What's my mode? Yeah, radian. Okay, good. Let's see if I do need to be in polar mode. I don't see a mistake. Yeah, the 3 before the integral. I didn't need to be in polar mode. I'm going to go back to my regular function mode. And I can just hit second delete and insert that 3. Second delete 3, enter. 9.424. Yeah, I think it works. Thanks, Sava. Thanks, Terrence. So I also imagine that there were a lot of questions that need to be answered regarding like sequences and series and some of those problems. And let's for sure cover that next time. I'm around per the normal office hours or by appointment. Keep striving for a 5. Is 9.425 the right answer? Okay. So that is a crash course, ladies and gentlemen, of parametric, polar, logistic. And we have now, I think, covered every topic. Whether or not it's been covered in depth enough for us is another thing. And that's why we still have a few months and a few more mock exams and a few more times of getting together, and then more per your request if you want to come by. It speaks volumes for you guys showing up on a Saturday, and I'm proud of you. I believe in you. Is there any questions before we end here? Isabel.
With everyone saying that we might be going back to school, will your office hours be affected by the hybrid schedule? Will that be changed, or will you still be there?
No, I plan on teaching my classes the same as I do now in hybrid. I plan on just being in school on my desk, and on our schedule is going to stay the same. My office hours will stay the same. Since we can't move around the rooms when we go back, I'm just going to be sitting in my danger zone. If you've been in my room, you know I have a danger zone, and so I was actually prepared for COVID, 6 years ago. Not really. Nobody could have, been prepared for this. But in terms of just having the taped off area, so to speak, I don't know. I think it should hold true. Thanks for checking there, Isabella. Also, folks, I have not been briefed on this year's exam in terms of how it's going to look in person versus virtually. If you're a junior, we're thinking of letting you guys take it in person. let me hold off on any of that. There's 3 dates. Have you noticed that? Did you get an email that there's 3 dates of the exams? For seniors, we want to do it on the second date because the third date is your graduation. And then for juniors, you're going to take it on the third date. That's the yes. And if you still prefer to take it online, you can. I just think it might be better to take it in person, but I know that safety concerns are warranted. But they plan on keeping the distancing very high and the air circulation and things like that. But we still have plenty of time before that happens. So let's see how the rest of February and March goes. I think the later, the better, so that we can get more practice in. I know Terrell wants you to take it sooner, but I think for me, I want us to practice more and study more. And I don't think the delay in taking the test is going to hurt us because we've learned the material with a conceptual framework. We've learned it through logic, and that never really leaves you. At least that's my hope. Other questions? Good one, Isabella, before we end. All right, it's a nice day out there. Make sure if you go outside, put on sunscreen, but enjoy it. And let me know how I can help you the rest until the next time. I think we're going to meet in 2 weeks. Okay. Thank you. Take care.
Do you have a nice weekend?
Thank you, Mr. Gordon.
Thank you, Mr. Gordon.
Bye. Thank you, Mr. Gordon.
My pleasure, guys.
Thank you, Mr. Gordon. Have a good weekend.
Thanks, Claire. You too. Oh, sorry, Renoa. It was Claire's face that I saw. See you, Renoa.